Okay, here we are, and I'm going to try something different. It'll make me feedback. I pull this a little farther away, down a little bit. Okay, so I heard you saying that these video lectures are a little hard to hear, hard to understand. So I'm going to try something a little different here, different room. Using the same microphone, I'm going to play it back and see what it seems like. And I'm talking too fast. Okay. So this is going to be blood pressure 3. Blood vessel 3. Okay, so here is where we left off. And this is talking about right now about total blood flow, pressure gradient over the resistance. So there's a direct relationship between the pressure gradient, between the pressure at this part of the blood vessel and blood pressure at this part. So the higher the gradient pressure gradient, the more flow. Resistance is in the denominator, so it's an inverse relationship. The greater the resistance to flow, the less the blood flow. And that's generally due to size of the blood vessel. The smaller the opening, the less blood flow. The greater the opening, the more blood flow. Now this is reversed. Don't get this confused with blood pressure. That is opposite for blood pressure. The smaller the opening in the blood vessel, the higher the blood pressure. Lower the smaller opening, the lower the blood pressure. This is blood flow. How much blood is flowing to the vessel? Okay. Factors that increase total blood flow, cardiac output, increase in cardiac output, increase in blood flow. Vasodilation, larger opening of the vessel, more blood flow. Factors that decrease total blood flow. Same two things, opposite. Decrease in cardiac output, decrease in blood flow, decrease in the size of the opening of in the blood vessel, vasoconstriction, the lower the blood flow. Okay. All right, switch it. Come on. How come it's not working out? Okay. So let's look at the regulation of blood pressure and blood flow. Neural control. Now, is it going to be neural controls and it's going to be hormonal control? The neural control are the cardiac and vasomotor centers in the medulla oblongata. And you need to know where these control centers are and the input to them and the output. Input is visceral sense, really. Barrow reflexes and chemoreflexes. Barrow means pressure, so these are stretch receptors, and generally in the carotid bodies, the carotid sinuses, and in the arch of the aorta. And there are chemoreflexes. This is basically detecting the pH of the blood. They're a little more important in the respiratory system, but they affect blood pressure and blood flow as well. And that is, if there's too much carbon dioxide in your blood, your blood is too alkaline, and you have to breathe, you have to breathe more rapidly, get more blood to the lungs to get rid of the carbon dioxide, and so on and so forth. Okay, output is sympathetic and parasympathetic fibers coming from the this is cardio-acceleratory center. So there's a cardiac center in your medulla oblongata. Part of it is cardio-acceleratory, that if you stimulate that, their heart rate will go up and blood pressure will go up. And that's sympathetic. Counter-inhibitory is parasympathetic. It will send out information along the vagus nerve, and it will cause your heart rate to go down. So that's the counter-inhibitory center. Now it works. Then there's the vasomotor center. And vasomotor means controlling a smooth muscle in blood vessels. So, and this is purely sympathetic. It's important to remember that blood vessels are innervated only on the sympathetic nervous system. That's it. So how constriction works is you stimulate the sympathetic nervous system. Well, let me get that. The nature of the effect, whether sympathetic drive either constricts a blood vessel or dilates a blood vessel, is dependent upon the receptors, the adrenergic receptors. Adrenergic receptors, remember, bind norepinephrine. And the postganglionic fibers of the sympathetic nervous system secrete norepinephrine. And remember that there are, last semester there are two different types. Actually, there's a lot more different types, but we're just going to look at beta receptors and alpha receptors. So beta receptors are found in skeletal muscles, coronary blood vessels. Stimulation then causes dilation. And actually, and this just actually, what it does is it inhibits smooth muscle from contracting. And so the smooth muscle relaxes, and the blood pressure inside the blood vessel then pushes the opening wider. So this is actually a turning off of sympathetic stimulation in this sense will turn off smooth muscle and make it relax, and the blood pressure inside will cause it to dilate. Alpha receptors are found in all other vessels. And this stimulation will actually stimulate the contraction of smooth muscle. And that'll cause vasoconstriction, small opening, and blood pressure will go up. So if your sympathetic nervous system is really fired up, you get a lot of blood flowing to skeletal muscles, coronary blood vessels, and brain. Actually, you should put brain in there. But all the other organs, their blood flow is being restricted, and your blood pressure is going up. If you have sympathetic stimulation all over your body, even though you're letting more blood into some areas, most of your arterial system is constricted, and your blood pressure will go up. And you need a higher blood pressure if you're in a fight or flight situation. Okay, just the sympathetic nervous system. Okay. So, results of stimulation of vasomotor center is changes in peripheral resistance. Okay. Peripheral resistance is how hard is it to get blood through arteries, and for most arteries in the body, if you stimulate the sympathetic nervous system, you get a smaller opening, that raises the blood pressure. Changes in circulating blood volume. So in places where we have vasoconstriction, blood, where is blood going? These are pretty much the same. Changes in distribution of blood flow, changes in distribution of blood volume. Where's the blood going? Well, it's going to the places where the arteries are dilated. And less blood is going to the places where the blood vessels are constricted. Okay, so what happens? if blood pressure drops in a barrel reflex, in a baroreceptors, blood pressure drops, then these stress receptors are not as stretched as they should be. And so tell the brain, okay, the blood pressure is dropping. We need to cause vasoconstriction. In blood vessels, we have to stimulate the heart sympathetically to raise cardiac output. Blood pressure increases, that means it's stretched too much. And this is the opposite signal to tell the vasomotor center to dilate blood vessels over the body and decrease cardiac output, to decrease blood pressure. Chemofactors, as I mentioned, respond to carbon dioxide and pH levels. They respond very weakly to oxygen levels. Oxygen has almost nothing to do with it. We'll find out that's almost paradoxical in the respiratory system. What controls how often you breathe? Oxygen's got practically nothing to it in a normal situation. They respond to carbon dioxide and pH. If it's not enough blood going to your lungs, your carbon dioxide will go up, and your pH level will also go up, even more outlet. If it's too much blood going to the lungs, you're getting rid of too much CO2, your blood will become acidic, and then you have to slow things down. Okay. Also, what else affects blood pressure is higher brain centers, the hypothalamus and the limbic system in particular, because this controls autonomic nervous system, which controls blood pressure, and the limbic system is the emotional center where strong emotions, good or bad, can really affect blood pressure. Can cause constriction or vasodilation and affect your heart rate. So the higher brain centers can affect blood pressure. And here is a very important. I should have brought that book. Should have what pages is on. Hang on a second. I'm going to pause. Okay, this is on page figure 20.14 on page 810. And it's really important because it shows you the whole feedback loops for maintaining blood pressure. So we have the aortic bodies, contain chemoreceptors. We got the carotid sinus carotid bodies, baroreceptors and chemoreceptors. And so they are in the yellow here, and they're bringing sensory information, visual sense, into the medulla oblongata. And then in the medulla oblongata, you can see the cardiac center with the two parts: cardio-acceleratory center, sympathetic, cardio-inhibitory center, parasympathetic, and the vasomotor center. So this is the autonomic nervous system. Now and the motor, so this is sensory input, yellow, motor output, sympathetic output, brown, and blue, preganglionic and postganglionic, and then green for parasympathetic. So here, the green is the vagus nerve. The vagus nerve is a mixed nerve. It brings sensory information from the baroreceptors and then motor output along the parasympathetic nervous system to the SA node, to the AP node, but not to the body node. that will slow the heart down. Here, and remember, this is the pre-ganglionic fiber for the circulating system. And there's a little tiny post-ganglionic fiber down here, which I know you put in. Sympathetic is different. It comes out of the it comes down the spinal cord out to a sympathetic chain ganglion, and then it will go to the SA node and AV node. You don't show it going to the AV node, but it goes to both. It also goes to the heart muscle. So this will speed up. And also, there's a motor center. This is also sympathetic. Blood vessels will only integrate by sympathetic nervous system. It either cause vasoconstriction or vasodilation, depending upon the nature of the receptor in those particular blood vessels. All right. Come on. All right. Okay, so there are two purposes of vasomotion. Generalized raising the overall blood pressure. You got a lot of vasoconstriction all over your body, your blood pressure is going to go up. If you have, that means peripheral resistance is high. If you have blood vessels all over your body that are dilating, this is going to decrease peripheral resistance and lower blood pressure. And also, modifying blood flow to particular areas, organs, and body that need it more than other organs. So, so as far as blood flow all over your body, you can't send every organ maximum amounts of blood. You haven't got enough blood to go on. You have to make, actually, your body makes minute-to-minute decisions as to where to send blood. What organs need it more than others, depending upon need. A great example is exercise versus digestion. You start exercising, your sympathetic nervous system is turned on, the blood vessels in your skeletal muscles will dilate. If there's lots of blood to the heart, coronary blood vessels dilate, there's more blood there. But remember, that will decrease blood pressure. When you have lots of blood vessels dilate, decrease blood pressure. You have to maintain blood pressure. So if you dilate blood vessels in one part of the body, you have to constrict blood vessels in another part to maintain blood pressure. So, digestion. You know, we need your digestive system or your urinary system if you're out there exercising. So those arteries are constricted. Versus the other side. Say you just had a nice big dinner, you're sitting down. Your skeletal muscle doesn't need a lot of, if you're sedentary at that point, you don't need a lot of blood to skeletal muscle, but the digestive system needs it. And your urinary system, you're going to have to lose some weight. So now, so the blood vessels to coronary blood vessels will probably be reduced to the blood vessels to skeletal muscle will be reduced because you open up a lot of arteries to the digestive system. It's going to lower blood pressure. So you have to constrict somewhere else, not constrict the skeletal muscle because you don't really need it. Okay, make sure I'm not. Okay, so here's the same thing again. Here's how blood flow can be really different in different parts of the body depending upon the needs at that moment. As I said, at rest and strenuous exercise, total blood flow is up here. So if you're just at rest, your blood gets 650 milliliters per minute. Or 250, skin 400, skeletal muscles 1100. You don't have to memorize these numbers, but just realize that about where they are. A kidney 1100, abdominal organs 1300, others 450. Okay, that's at rest. Look what happens strenuous exercise. Increases and decreases. Weight increases a lot, not a little, just a little. But your heart gets 3 times, your skin lots more because you want a very hot blood to the surface because you're doing a lot of heat. And look at skeletal muscles, 12,500 from 11. But what don't you need? So you got that whole dilation there. Blood pressure is going to drop over the body. You don't need these when you do a strenuous exercise. So abdominal organs decreased 1,300 to 600, kidney down from 1,100 to 600. So this is distribution. This is vasomotor, distribution of blood to where you need it most, depending upon what you're doing at that moment. All right. And hormonal control. Let's stop it here. So neural control blood pressure. Now we're going to hormonal control. Let's put that in the next video. So let's stop it here. I'm going to check it out to see whether this video is a little better than the others. Okay. So I'll see you in a little bit. Where am I?